Hello, I'm Bryce Adelstein Lelbach. I've worked on programming languages and compilers for over a decade. I've served as chair of the Standard C++ Library Evolution Group, which designs and standardizes the C++ standard library. I'm a principal architect at NVIDIA, where I drive our strategy for HPC programming models, C++ compilers, and C++ libraries. And I'm here today to talk to you about the future of C++. C++20 was the largest release in over a decade. It delivered 4 major features: modules, coroutines, concepts, and ranges, and dozens of other additions and improvements. C++20 is now widely available, with most implementations shipping most of C++20 in production. We're seeing increasing adoption and more projects and organizations switching to C++20 as their default. The next standard, C++23, shipped back in February. There's a lot of exciting changes coming in C++23. To name a few, enhancements and additions to ranges, which were added in C++20, formatted output, MD-span, a multidimensional array abstraction, expected, a new error reporting paradigm, standard library modules, and deducing this. In the months leading up to a new release of C++, our focus is often on what makes it into that release and what doesn't. We put longer-term goals on the shelf. Today, I want to dust off those longer-term goals. Let's look beyond C++20 and C++23. What's next for C++? I want to tell you about 3 features that we're working on, features that I think will revolutionize how we write C++ code. And those 3 features are reflection, pattern matching, and senders. Our exploration today will focus on what we can do with these facilities, not the specifics of the committee proposals or the merits of different design decisions. This is a talk about possibilities, not details. Much of what I'll show you is tentative and in some cases speculative. In places where the design is uncertain, I've chosen the option that makes the most sense to me, and I've ignored the alternatives. This talk represents my own views. I do not speak for the committee as a whole. No one can. First, let's talk about reflection. Metaprogramming is the craft of creating or modifying programs as the product of other programs. Reflective metaprogramming is metaprogramming that incorporates data from the program being modified. There are 3 components to reflective metaprogramming: reflection, extracting information from the program; compile-time programming, tools for manipulating that information; and injection, inserting new program entities. Let's look at a simple example, a function that takes an enumerator and returns its name as a string. We're using a few new C++ constructs here. The reify operator takes a C++ entity, a function, a struct, an enumerator, a variable, a namespace, etc., and produces a reflection. A reflection is a handle to an internal compiler representation of the type T. Std metainfo is the type for reflection objects. Reflections can be manipulated and transformed just like any C++ objects. Here, we pass the reflection of the enum type T to the function meta_membersof. Meta_membersof returns a metainfo that represents all of the enumerators of T. Such a metainfo object is a range, so we can use a range-based for loop to iterate through the elements. we want to use the new compile time expanded for loop, template for. Each element may be a different type with a template for, which a normal for loop wouldn't allow. In each iteration of this compile time for loop, we want to check if the enum parameter of the function is equal to the value of the current enumerator. To do that, we need to take the reflection of the current enumerator and turn it back into a real entity. We can do this with the splice operator. The splice operator takes a reflection value and turns it back into the entity that it represents. In this case, the enumerator in question. If the parameter is equal to the current enumerator, then we need to return its name. We can get that name with another function that operates on reflections, meta name of. And that's it. Here's another example, hash append, a hash protocol that incrementally passes input to a hash algorithm. It takes a hasher object and an object to hash. First, we reflect on the object we're hashing and use the members of function to get all of its members. The members of function takes an optional parameter which filters for certain kinds of members. In this case, we only want non-static data members. Next, we do a template for loop over all those data members. We use the splice operator to access the data member. And we recursively call hash append on the member. We can also inject at class scope, allowing us to build powerful wrappers. This traced class wraps another type, adding a print call before invoking each of the underlying methods. Traced has a data member of the wrapped object. We use a template for at class scope to generate a member for each member function of the wrapped type. We inject the protection, attributes, and return type of the member that we're wrapping. Next, we need to name the method that we're injecting. We can't use the regular splice operator. It would inject the method of the underlying type, but what we want is to create a new method in traced with the same name. Think of the regular splice operator as injecting something akin to a pointer to member. We can only use it on an object of the underlying type, not on our wrapped type. Instead, we use the identifier splice, which operates at the lexical level and inserts a name. Now, we need to generate the parameters for the method. Here, we use splicing pack expansion. Adding triple dots before a splice will cause it to expand to a parameter pack-like construct, which can be unpacked with a trailing sequence of triple dots, as shown. Then, we inject the qualifiers of the underlying method. Finally, we generate the body of the wrapping method. First, we print out the name of the method we're calling. Next, we generate the call to the underlying method on the underlying object that we've stored. Note that here we use the regular splice operator, not the identifier splice operator, because we're operating on an object of the type that we're reflecting on. We forward all parameters, and we inject the names of the parameters, again using splice pack expansion. Here we use the identifier splice. We're referring to the generated parameters of the wrapping method, not the parameters of the underlying method. And with that, we're done. Reflection can be a powerful tool for automating data layout transformations and optimizations. One common transformation that can have huge performance impacts is switching between array of structs, where data is stored as a single sequence of multi-component elements, and structive arrays, where data is stored as one sequence for each separate component. Switching between the two usually requires structural code changes. Array of structs is often more intuitive, but structive arrays usually offers better memory access patterns, which can be critical when parallelizing or vectorizing. Consider this code, which applies an operation to just the red channel of a sequence of colors. It will have a strided access pattern, and in some cases may have alignment issues which inhibit vectorization. We can use reflection to write a wrapping type that automates transforming from array of structs to structive arrays. First, we get the non-static data members of the type that we're wrapping. Then, we inject a vector for each data member of the underlying type. This constructor initializes the wrapper from a range of the underlying struct, or the array of struct data. We use a template for to iterate over each of the component vectors. For each component vector, we resize it, and then we copy from the range of array of structs data. We can make our wrapping structive arrays type a range of tuples of references to the components so that it can be iterated as if it was array of structs. For example, to write an indexing operator, we use the identifier pack splice operator to get a pack to the element in each of the component vectors at the specified index. Then we use tie to return a tuple of references to those elements. The same approach can be used to create actual iterators, but in the interest of brevity, we're not going to look at that in detail. I think this is enough to illustrate the general approach. Now, we can take our natural and intuitive array of structs code, and by simply changing the type of image from vector to SOA, we've switched the code from array of structs to structive arrays. This changes the memory access pattern for our single channel operation from strided access to contiguous access, which is more cache efficient and easier to vectorize. Reflection will fundamentally change how we write C++ code. Reflection will help us solve problems that today often require boilerplate, macros, or external code generation. Things like serialization, protocol and language bindings, instrumentation, logging, debugging, etc. It will change how we build and design libraries and how we evolve the language itself. Now, let's move on to pattern matching. C++ has two selection mechanisms today. Switches operate on a single integral value, which is often too limited. You can't use them with string literals or objects. If statements, on the other hand, operate on arbitrary Boolean expressions. They're powerful and can express almost anything, but they're often too complex and verbose. We need something in between the two, a powerful but concise way to select and decompose objects. That's what we get with inspect, a new selection mechanism for C++. Inspect matches values against patterns and binds variables when matches are successful. Inspect is an expression, not a statement. An inspect expression takes a parameter, the object to select against, and a series of patterns. There's a variety of different patterns available. I'll highlight a handful of them today. Each pattern is followed by a statement which is taken if the pattern matches. Inspect stops at the first match, not the best match. Constant patterns match if the object is equal to the constant. And the wildcard pattern will match anything. Constant patterns aren't limited to integrals or enums. They can be strings or any arbitrary object. Here's another example. Fibonacci written with inspect. Here we use the identifier pattern, which binds the value to a name. Pattern guards can be used to perform arbitrary tests for a match. Since C++17, we've been able to destructure tuple-like objects. We can do that with inspect too, with compound patterns. This compound pattern consists of three constant patterns. It will match if the object can be destructured into three components, like a tuple, and each of those components is equal to the corresponding constant. On the other hand, this compound pattern consists of three variable patterns, so it will match anything that can be destructured into three components, regardless of their value. Alternative patterns can match different types and variant-like objects, any-like objects, and polymorphic objects. They give us a much cleaner way to work with variants. Instead of writing a visitor and calling std_visit, we can just inspect the variant and use alternative patterns. We can use alternatives to match a polymorphic object against different classes. Here, we have a circle class and a rectangle class, both of which inherit from a shape class. When inspecting a shape, we can use a combination of the alternative pattern and the compound pattern to determine whether the shape is a circle or a rectangle, and decompose it into its defining characteristics at the same time. Alternatives can also be useful when working with dependent types in a template. Extractor patterns allow us to completely customize matching and decomposition by implementing our own extractor protocols. An extractor is an object that has either an extract or try-extract method. When an extractor pattern is used, this method is called with the value under inspection. And then if the result of that call has a value, it is matched against the child pattern. For example, In the first pattern in this inspect, phone_number.tryExtract will be called, and if it returns a value, that value will be matched against the compound pattern here. Let's look at a more detailed example that combines the power of pattern matching and reflection. We're going to write a simple function to serialize C++ objects to JSON. Our function will take an object that we want to serialize and return a std string. First, we create the string that will fill with the JSON. We add an opening brace to it, which will close at the end of the function after we've filled it with content. Next, we'll get a meta info listing all the non-static data members. And we'll iterate through it with a template for. We output the name of each member. And then we inspect the member to output its value. If it's a bool, we output either true or false, as those are constants in JSON. If the member satisfies the numeric concept, then we output it as a number using the default formatting. If it's a pointer and it's equal to null, then we output null, which is a JSON constant. If it's a non-null pointer, we just output its address. If it's something convertible to a string, we output it in quotes. If it's a range, we recursively call saveJSON on each element of the range, and then use format's default range formatting, which outputs a JSON list. Finally, if the member is something else, we just recursively call saveJSON on it. And we add a comma after the member, unless it's the last member. And finally, after we've done that for each of the members and added the closing brace, we return the string. In just a few lines of code, we've written a powerful and generic serialization function using pattern matching and reflection. Writing this today would be a lot more verbose and would likely require each type to opt in and provide its own serialization function. Inspect gives us a powerful new way to select and decompose objects. It makes working with tuple-like and variant-like objects far more natural in C++. It will revolutionize how we write C++. Expressing conditional logic will be simpler and far more natural. Finally, let's talk about asynchrony in C++. Today, C++ has no standard model for asynchrony and no standard way to express where things should execute. That's why we're introducing senders, a model for asynchronous execution in C++. There are three key concepts in the senders model. Schedulers are lightweight, non-owning handles to execution contexts. Schedulers produce senders. Senders represent asynchronous work that will eventually send a signal. A signal is either success and a set of values produced by the work, failure and an error produced by the work, or cancellation. Senders can be composed together with sender algorithms to form task graphs. Receivers are connected to senders and process their asynchronous signals. Let's look at a simple example. First, we need to get a scheduler from somewhere. This could be a thread pool, a tasking system, a GPU driver, etc. To start a chain of work on that scheduler, we call schedule, which returns a sender. That sender will complete on the execution context associated with the scheduler. Next, we use a sender algorithm, then, to compose work onto the sender that we got from the scheduler. This work will be performed on that same execution context. The sender algorithm will return a new sender, which we can use to add more work onto the chain. Finally, we wait until the chain of work has completed using sync wait, which will return the value sent by the final sender in the chain. The pipe syntax gives us a clean way to compose chains of senders in the order that they will be evaluated. Now, let me show you some of the most important sender algorithms. Sender adapters are a type of sender algorithm that take one or more senders as parameters and return a sender. Most sender adapters are pipeable, just like range adapters. The semantics are similar to Unix shells. Languages like Haskell and APL call this point-free style. The primary input argument is not explicitly named. Then takes an invocable, f, and calls it with the values sent by the prior sender. The sender returned from then will send the results of the invocation of f. This is how you attach a continuation to a sender. Bulk is similar to then. It evaluates the invocable once for every index in the shape n. In the simplest and most common case, the indices are one-dimensional and start at 0, and the shape argument is an integer indicating how many invocations to perform. The sender returned from bulk will pass along the signal from the prior sender. Transfer changes the scheduler that will be used for the next sender. It doesn't change the scheduler for the prior sender. Some senders can only be connected to a single receiver. For example, because they move any values or error they send instead of copying them. We call these one-shot senders. Senders that can be connected multiple times are called multi-shot senders. Split takes any type of sender and returns a multi-shot sender that passes along the signal from the original sender. Split senders represent forks in a sender task graph. Conversely, WinAll takes multiple input senders and returns a single aggregate sender that will send signals from all of the inputs. Senders returned by WinAll do not have a scheduler associated with them, which means they do not promise where they complete. WinAll senders represent joins in a sender task graph. WinAll is not a pipeable sender, as the partially applied piped form would be ambiguous with the fully applied non-piped form. Ensure started connects and starts a sender, returning a new sender that will pass the signal sent by the original. If the input sender is a composition containing other senders, those senders will be connected and started as well. Sender factories are another type of sender algorithm. They do not take senders as parameters, but they do return a sender. Sender factories are used to start new chains and graphs. The senders they return are the root nodes. We've already seen one sender factory, schedule, which returns a sender that completes on the specified scheduler. The return sender doesn't send values or represent any actual work. It's just a handle you can use to compose work on the scheduler. Just is another sender factory. It takes a set of values and produces a sender that will send those values immediately when connected. The last kind of sender algorithms are sender consumers. They take senders, but do not return senders. They typically launch a sender graph by connecting and starting it. They are the leaf nodes of sender graphs. SyncWait is a sender consumer and synchronization primitive that blocks until a sender completes, and then returns or throws whatever was sent. We've developed a prototype of senders that supports CPU schedulers, GPU schedulers, and distributed schedulers. This simple electromagnetic wave simulation solves Maxwell's equations on a uniform grid. This is the entire solver loop, which is expressed as a graph of senders. This code can be run with a variety of different schedulers. By changing just one line of code, the kind of scheduler passed to the solver, we can go from running inline on a single CPU thread to running in parallel on the CPU using OpenMP, to a single GPU, to multiple GPUs within a single node, and to multiple nodes, scaling up to thousands of GPUs. We've ported a simulation from the Plabos Fluid Dynamics framework to senders. This simulation models carbon sequestration techniques. The porous structure you see is sandstone saturated in salt water. The red bubbles are liquid CO2, which is injected at the bottom and travels through the sandstone because of buoyancy forces. Using a distributed GPU scheduler, we've run this application on up to 512 GPUs. With standard C++ senders, you can change one line of code and scale from a single CPU thread up to an entire cluster of GPUs. Let's look at an example from the networking world, an asynchronous read of an array of data of unknown length. We'll use this dynamic buffer type to store the data we read in a unique pointer, as well as the size. Our async read array function will return a sender which sends a dynamic buffer. It will take a handle to whatever network library we're working with. We'll start our sender chain by introducing a new dynamic buffer object with just. Next, we use a letValue sender adapter to create a scope that will keep the buffer alive for as long as we need it. Now, the first thing we'll need to do is figure out how big the array will be. We'll expect that sender will send a size t that contains the size of the rest of the data. We'll need to read that first. So, we get a span to the size member of the dynamic buffer. Then, we call async read, a sender adapter that expects a span and reads into it. async read will send the number of bytes read. We'll add a then, which will do three things. First, we make sure that we read the number of bytes that we expected, a size t's worth. Next, we will allocate that many bytes in the unique pointer. Finally, we return the span to that storage. Now, we're ready to do a second async read, which will read the actual data. After that read, we have a second then, which will confirm that we read the number of bytes that we expected. And with that, we're done. Now, let's look at another example, a generic, asynchronous, and parallel inclusive scan. It'll take three parameters: a sender, which will expect to send the input as a range, an initial value, and the number of tiles to split the input into. We're going to use the classic two-pass parallel scan approach, which requires temporary storage for partial results communicated between tiles. We need to allocate this temporary storage asynchronously once the prior sender has sent us the input. So we'll chain a then sender onto the prior sender. In the body of that then, we'll create a vector to hold the partial results. We'll return both the input range and the vector. Next, we need to do the first parallel pass, the down sweep. We'll use bulk to invoke the body of the pass for each of the tiles. The first thing we do for each tile is calculate the range of elements that belong to the tile. Then, we take all of the elements in each tile and perform a local serial inclusive scan on them, which we do right here. Next, we need to propagate information between the tiles. The sum of each tile needs to be added to the elements of all subsequent tiles. We've already computed that sum. It's the last element of the local inclusive scan. We store that result into the partials vector. Assignments to partials from different tiles may happen concurrently, but that's fine. Each tile uses a different and unique slot in partials, and no one reads from partials yet, so there's no data race here. Then, after all the tiles have completed their local inclusive scans and written to partials, we need to have one execution agent do a serial inclusive scan of partials. We do this by piping another then sender onto the chain, which will perform the partials inclusive scan. This then sender will again pass along the input sequence and the partials vector. The result of the scan over partials looks like this. The information that each tile needs to add to its elements is in the partial slot for the tile directly preceding it. Now, we need to go parallel again to distribute that information within all tiles. This is the upsweep pass. So, we'll pipe another bulk once again over all tiles. In the body of this bulk, we'll need to calculate which elements belong to the current tile, just as we did before in the downsweep pass. Then, we'll use a serial for each to increment each element in the tile by the appropriate value from the partials vector. After that addition, we'll have the correct result. Finally, we want the sender returned by our asynchronous inclusive scan to only send the input sequence, not the partials vector. So we add a final then sender which only passes along the input. The partials vector, which we no longer need, will be destroyed when this then sender completes. And that's it. We're done. We've got a generic, asynchronous, and parallel inclusive scan that we can run on any scheduler we want. Reflection, pattern matching, and senders. I believe these are the three most exciting C++ features that we're working on. Combined, they'll radically improve how we express ourselves in C++ and allow us to elegantly solve problems that are challenging today. Finally, I'd like to thank everyone who's worked on the features that I've discussed in this talk or otherwise helped me prepare this material. Thank you for your time and attention. Feel free to contact me if you want to learn more about or get involved in the development of C++. You can also check out my other talks on YouTube and my podcast, ADSP.